Okay, this is an example of a looks like a microchannel condenser that you would typically see in current air conditioning systems. And I'm kind of curious to see what they are calling this. Okay, this is going to be found on page 1069, figure 36.17 is a microchannel coil courtesy of Modine Manufacturing Company. If you look at that thing closely, it resembles what you would see in automotive radiator technology today. Look at how tiny these openings are as far as circulating fluid. This is quite something. From a refrigeration standpoint, if you get a leak in one of these things, they can be repaired, they can be pinched off, but it's a lot of work. Typically, I will not attempt repairs on these microchannel coils. I will turn them into the manufacturer's distributor for warranty replacement. Here we have an evaporator coil, which we talked about earlier. This is an A-frame type coil. Notice that the TXV is over here, and you have a distributor that has several circuits. It's a little hard to see without blowing this picture up. And then, of course, here you have your refrigerant connections. One is going to be the suction line. The other one is going to be the liquid line right up here. This is a slant coil design. I've seen these a lot on Carrier BDP products. They work reasonably well. The only thing I have an issue with these things, if they're not mounted in the correct position, some of the moisture may not run off and collect in this drain pan and end up in the floor of the return air cavity and create moisture and mold issues. This is airflow is very critical on this slant coil design. This is an example of what they call a slimline condensing unit. You're going to utilize this type of technology. In fact, I'm doing a job in Rancho Cucamonga next week utilizing this very same footprint. The thing with this narrow profile condensing unit is typically they're less than 24 inches in width, and I'm talking about front to back. These things typically are about 4 feet high. And then, of course, the condenser fan is mounted in a horizontal position. The one thing you have to be careful of is you don't want to put any plants around here, because the hot air that this thing is going to blow across the front of this unit is going to kill your plants and stuff. So be aware of that. The compressor sits over here. The controls sit up here. These are very easy to service. They work very, very well. I've had no real issues with them at all. This is an example of a standard air conditioning unit. Typically, you have your condenser on either 3 or 4 sides. The service access is either from the back panel, or everything has to be serviced by taking out the fan at the top. These units tend to be on the large side, typically 36 by 36 as an example, and typically about 3.5 to 4 feet high on average. This one here can be a copper and aluminum design. Some manufacturers have chosen to keep this design. Other manufacturers have gone to microchannel, all aluminum design. It really depends on the company. I have installed York products. I'm just going to say they're okay. I'm not going to give you my personal opinion about them. This is an example of a horizontal evaporator coil. Basically, you have a transition from your furnace or air handler in the to this horizontal coil, and then on the discharge side of that coil, you will have a large plenum where you hook up your ductwork to. The problem with this type of design, this is a lot more field fabrication involved. They do a very good job. I've installed them in the past. They're just really hard. It's a lot of work from an installation standpoint. I prefer to use a what they call the ductboard coils where you have the coil, which is an A-frame inverted, and you would have the ductboard in front of it where you can take and hook up your ductwork to it. That's very popular in the installation of new homes and replacement work. These, they're not going to see very often, but I will tell you they're out there. And if these things get dirty, you have to take all the ductwork apart to gain access to them. I haven't had any issues other than the fact that they're hard to install. My very first install in my house in Pasadena utilized this type of coil. I will tell you, it took a while to get that in. Okay, here we have a TXV. Notice that we have a liquid line going in. We have the thermal bulb, which is mounted on the outlet horizontal plane of the suction line. This is the equalizer connection, which is also mounted next to the bulb location. And here we have a distributor, and then we have these circuits. In this case here, we have 3 circuits on this evaporator coil. The one I worked on today in West Covina had 6, and circuit number 6 developed a leak on the capillary line because that line was submerged in the condensate tray. So just be aware of that. Here we have a swamp cooler. This is a window mount we talked about in the previous presentation on the PowerPoint. Here we have a, I believe this is a discus compressor from Copeland Corporation. And notice that the suction gas is going to be hooked up to this end bell right here. And then you have your discharge is going to be up here on the top of the valve plate. And over here we have a what they call Centrec oil failure pressure switch. Down below here is the oil failure switch. And to check the oil level on this discus or a Copeland type compressed, yeah, this could be, this one's Copeland, but Carrier makes the same thing. You basically you'll check your oil level right here. Typically your sight glass should be about half full when the compressor is operating. When this thing starts up, you will probably see a lot of violent foaming that's taking place. And the reason is the refrigerant mixes with the oil. And this is important because the oil and refrigerant need to separate out. That's why you utilize a crankcase heater. If you don't do that, the liquid will affect the lubricating quality of this compressor oil and shorten the life of the internal wearing areas. Okay, this is the internals of a hermetic compressor that you would see in a lot of AC refrigeration systems. Notice that you have your motor winding up here. You have your suction pickup tube up here. You have your internal spring mounts to keep this thing isolated. I've actually seen these springs break because of liquid refrigerant coming in here. And what happens is when they break, these windings sometimes have a tendency to ground out against the, I would call this the pot or the panel that covers the hermetic unit. Typically, this is a 2-piece construction, bottom and top shell, and of course they're welded right here in the middle. I have taken these things apart for just inspection. It's an awful lot of work. So typically when a compressor fails, just take and figure out what the failure was. Was it electrical or was it refrigerant related? Make the necessary corrections and install a replacement compressor. These compressors are very reliable. They do a very good job. I technically prefer the scroll design over the piston, but these work very well. This particular one here is made by Tecumseh. It's a company that's been around for a long, long time. And here I believe we have this appears to be a rotary compressor. I'll verify that. Rotary compressors are used a lot in, I've seen them in mini splits. I've seen them in window air conditioners. They do a very, very good job. They're very simple and they hold up a long time. So this rotary compressor is going to be found on page 1073 of your textbook under figure 36.21. Rotary compressor, basically these are your different components: your vane spring, your shaft, your bearing, your cylinder or pump chamber, the shell, of course, that's surrounded here. Your overload, which is internal. Electrical connections are always at the top. Discharge in this case is at the top. Here you have what appears to be a filter dryer on this mounted on the side, and your suction pipe is brazed in right here. Okay, here we have an example of the rotary compressor. Basically, take that. Yeah, this is the rotary compressor. Basically, this is going to be found on page 1074 under figure 36.23. And basically, this is going to be, of course, your housing. This is your shaft. Notice that we have this lobe or rotor, which is in an offset formation, and refrigerant suction gas is basically taken in here. And then this thing moves, and as it moves, it takes this gas, narrows the channel, and increases the temperature and the pressure. We also have a sliding vane valve here. And when these things break, typically these things quit pumping altogether. Then, of course, you have your discharge vanes over here, your discharge valve, and the refrigerant exits this compressor. Okay, I believe in this case here, this is going to be found on page 1075 under figure 36.26. This is the compression cycle of the scroll compressor. This is basically how a scroll compressor works. You have a fixed and an orbiting scroll, and the refrigerant basically is going, notice that the refrigerant enters, and as this thing spins in a high degree, notice how this the refrigerant is passed through and basically compressed towards the center. And of course, we talked about this picture here where you got the split system air conditioner and you have leaves that take and shed on here. This is found on page 1077, your book. It's 36.30. The air conditioning unit you see here is discharging air through the top, and of course the fan blades top. This is a very popular design right here, having the fan on top, coil on the sides. Of course, if we have leaves here, we are going to have a dirt and maintenance issue to deal with. So basically, if you look right here, this is going to be another picture. This is figure, this is below the 36.30. And what happens here, basically they're talking about how the fan blade has a thrust that takes place on this motor. Notice that the fan blade's in the up position, the shaft is in the up position. A lot of the current units that I currently work on typically have the shaft down position, which I think is superior in some respects. Okay, here we have an illustration showing the different locations. This is going to be found on page 1078 of your textbook, and it gives you locations for depending on the type of system, as far as where the air is going to get distributed. Typically for air conditioning, the best way is either up here on the ceiling or a high sidewall. Low sidewall is not technically ideal for a supply situation. It is great for heating. A floor register, again, is great for heating. I wouldn't say it's great for cooling. And baseboard register, they also work good for heating. I'm not wild about them as far as air conditioning. And then there's the window slot. I haven't seen a window slot type thing There's also the perforated grill. These are just different examples of how you get the supply air into a room. In order to achieve a maximum temperature exchange, I think the best thing to have is have the supply air either high or ceiling, and then have a low wall, sidewall return or a floor return, because basically you're forcing the heat to be drawn down here where you're at. I like returns near the floor. It works very, very well. The concept's very good. The problem is, depending on the building instruction, you may be able to incorporate it or you cannot. Okay, this illustration, I believe, is on. Let me find it here. Basically, it talks about the solar gain. I think we talked about this earlier in the previous PowerPoint presentation. But basically, what we're talking about here, notice how where the sun is in the morning on the east side and in the evening on the west side. And then, of course, the sun's right above in the center at noon. And typically, your heat gain is going to take place here in the morning, during most of the day up here in the attic, and then, of course, in the evening towards the west. Remember, heat builds up in attics, gentlemen. Heat builds up in attics. And the way to get that heat out is either through a powered exhaust method, natural method of going through the sidewall vents, or better yet, increase your insulation value between your finished ceiling in the house and have the appropriate amount of insulation to keep that heat up in the attic. But the thing is the more the heat's up in the attic, you're still going to have a constant heat load placed below it. That's one reason why I like these new panels, which I spoke about highly in the previous PowerPoint, where the aluminum coating on this plywood roof decking is affixed to this plywood to reflect the heat back to the roof instead of into the attic. It achieves considerable heat transfer savings in the summertime as well as the winter. It works very well. There's been some discussion about, does it shorten the roof life? Well, if you utilize asphalt type shingles, it probably does. If you have clay tile, whatever, then I don't think it's an issue. And here, this is another illustration showing the relationship of the sun in the summertime. And then, of course, in the winter time, it's a little bit different. So this shows you where you're going to end up with heat exposure in the attic at this point. Okay, once again, we talked about this slide previously. This is an example of using an attic vent fan. What I also noticed, now they have a solar panel or a solar assisted electric fan that does the same thing. The problem with the solar is the fan runs when the sun shines. When the sun quits shining, the fan shuts off. Okay, so that's great because during the day the sun shines and the fan is on. The problem is the fan's on anytime the sun is out or daylight. There's not an off-on switch or a thermostat necessarily. So be aware that if you purchase a solar panel. Okay, so if you take and purchase a solar panel type attic vent fan, be aware anytime the sun is out and generating power through the solar panel, this fan's going to be on. There's not necessarily a thermostat hooked up to keep the fan off on a cool day. This particular illustration shows the hot air collecting in the attic, and the air is drawn out of the attic through the natural process of heat rises and exits through either the side vents or a roof-mounted ventilator hood of some type. And the problem with this is the heat has a tendency to stay inside the attic forever. Okay, this is another issue. We have a lot of houses in Southern California that unfortunately have a very low roof line or not much of a roof line. I recall the time my parents lived in a house in Roland Heights that had no attic, and it utilized this type of construction. Basically, you had open beam construction, you had this insulation panel, which in my opinion was worthless, and then on top of that, you had a built-up roof. Now, here's the problem. The ceiling stays hot all the time, living space has no attic, and you've got to increase the cooling load based on this type of construction. If you are contemplating purchasing a house like this, I would highly advise you to think again. These types of roof construction where you have an open beam concept with an insulation panel between the roof deck and the ceiling below is going to be a problem as far as heating and cooling is concerned. I would strongly urge you to look at purchasing or investing in a structure that has an attic where you can take and separate the ceiling area from the roof line. Otherwise, you're going to have a hot house in the summertime. You will be running air conditioning practically nonstop. I noticed that you see this type of construction out in Indio as well as Palm Springs in older houses. I personally do not like it, and I have told people that I am not going to bid on projects utilizing this type of construction because the cooling load is very excessive. Okay, here we talked about this earlier. Notice that inside the house in Augusta, Georgia, it's 75 degrees Fahrenheit. Outside it's 90, the temperature difference 15 degrees. These are design conditions. And in Phoenix, Arizona, we have an inside temperature of 80 degrees. The outside is 105. We have a 25-degree difference as far as the difference between the inside and the outside. In Phoenix, typically we have low humidity to deal with. In Augusta, Georgia, on the other hand, we have lots of humidity. So this creates a separate set of problems that doesn't exist necessarily in the Phoenix metro area. So that being said, your insulation values and different building construction methods are going to be utilized to take and minimize the heat buildup, especially in the Phoenix Valley area versus Augusta, Georgia, where you're going to have to deal with the heat and the relative outdoor humidity. This is an example of an R410A split system. I work on lots of these all the time. So basically outside you have the condensing unit right here. It's easy on a concrete or a lightweight plastic pad. You have an access panel. This one here is a vertical discharge coil surrounding, and basically you pull air in at 95 degrees. And typically we should see a 10-degree split between right here and right here. Your electrical controls and compressor are located back here. And then basically our pressures are measured on the liquid line as well as the suction line. Because it's R410A, look what we're operating at on the low side. 118 PSIG, 473 PSIG on the discharge side. You have your electrical disconnect, and basically this is a normal. On a 95 degree, these are the pressures we would expect to see at the condensing unit. Then of course you have your liquid line, suction line, you have your upflow furnace, you have your cased coil on top, your ductwork above that, and we're going in the supply ducting at 55 degrees. We're coming back in return air about 75. So we are seeing about a 75, 55, that's a 20-degree split, which is ideal. And then of course it's the return air, and hopefully you have a filter installed to trap all the dirt. Okay, this is an example of looks like another scroll compressor here. I will see if the book makes reference to this. Just give me 1 second. Yes, it does. This is on page 1075 under 36.25. This is the orbiting action of the between the fixed and the orbiting scroll. And this shows you how the refrigerant comes in through the low pressure side, through the side, compressed, and then coming out through the discharge line in the center. That's your high pressure, high temperature gas. Enter through the side, exit out to the top. This is a very efficient design, very few moving parts. This is proven technology. I've installed lots and lots of these scroll compressors, and I will tell you they work very, very well, and they last a long time. This is a side view of a scroll compressor, and these things, like I said, they work extremely well. Your scroll plate, your fixed orbiting scroll, your motor section, and of course your refrigerant connections, your electrical connections are here. Okay, here there's an example of a typical split system, and this one here, condensing unit is outside. Notice that we have a basement in this house, which is something you don't see very often in Southern California. Maybe back in the Midwest or something, but not typically out here. So what makes this system unique, if anything? Typically, because we have the furnace and the coil, the refrigerant basically knows that we have a loop here. We're concerned about oil return coming back to this outdoor condensing unit. The furnace, of course, will be located in the basement section. Return air is either going to come through the back or the side connection. Your A coil is going to be mounted here. Your supply plenum is going to be up here. And the ductwork, which it doesn't show here, appears to be hanging under these floor joists, and you have your ductwork there. Now you have your return located by where this connection is. It doesn't show it in this picture necessarily, but that return air is typically where you want the thermostat to be located. The reason why we want it to be located there is simple. We want to be able to sense the actual air that is being returned to the unit. And this picture, by the way, can be found on page 1065 under 36.7. Okay, here we have a package unit, supply and return. In the perfect world, when you're replacing these, the only thing you're going to be dealing with, in theory, and by the way, this can be found in page 1078 under figure 36.33, and you're going to have two fan motors, one for the evaporator and one for the condenser. And notice that they have a this black area, which is a vibration eliminator. This is what they call a neoprene. Trying to remember that thing. It's a neoprene jacket that's mounted on sheet metal, basically to eliminate vibration between the ductwork and the package unit. There's a name that they called these things. I used to put these things in. It was a lot of work. This illustration is found on page 1079 of your textbook under 36.34. These are package unit installations, and basically they're showing round duct connections to the package unit, your side panels for access to the machinery, the blower, and of course is mounted on a concrete pad, your condenser coil, and of course your condenser fan motor, which has a vertical discharge. And then typically, if this unit's mounted on the roof, it's going to be mounted on a curb, and you'll have the ductwork either below it or attached to the side, and you'll have your disconnects, electrical disconnects, either mounted on the package unit or on the ductwork, depending on the job. And of course, you have your supply ducting, return air ducting. The big thing about the package units on the roof and package units on the side, it's extremely important to seal that ductwork because we don't want to air condition the outside of the building or heat it in the winter time. The ductwork has to be integral, has to be tight, has to be very well designed and waterproof. And very importantly, make sure that you have your disconnects for the equipment so it can be serviced. Okay, here we have a looks like an old carrier unit. I don't know if this picture is even still in the book or not. That's kind of interesting. They are showing the compressor. They are showing the, yeah, it's still in there. Okay, this is figure 36.27, which is found on 1076. Condensers can either have a copper or aluminum fins with aluminum, or all aluminum. So here you got a reciprocating compressor. In this case, we're utilizing copper tubing with aluminum fin construction, condenser outdoor fan motor, and of course your brass service valves where your refrigerant, liquid line, and suction line are mounted. Here we have a mini split. These things are quiet, they're efficient, they do a great job. My only complaint looking at this picture, look how close the coil is to the house. That is going to present a problem. The reason why I say that, you need to have airspace between the building and the coil in order to take and move air through the coil. The other thing you want to be able to do is wash this coil down on occasion in order to keep it operating correctly at its peak performance. If this thing's right against the structure, how are you going to clean that coil? The only way you're going to be able to do it is you're going to take this panel off the top and you can go from the inside out. But what am I saying? Read the manufacturer's service and installation instructions. They will give you a recommendation how far this unit is to be away from a wall. Luckily, this is a horizontal blade design, so you're pulling air from the back and discharging out through the front. That being said, we still need that airspace in order for this thing to be truly efficient. And of course, on the ductless system, this is what the typical wall, the indoor evaporator coil looks like. I have one in my train room. It's a 12,000 BTU unit and looks something like this. What I like about these mini splits, they're maintenance free for the most part. Occasionally you have to take and open up this door, take these filter elements out, wash them, clean them. And you have an oscillating feature where these things can move side to side, up and down in order to distribute that cool air in a structure. Very important that you size a mini split to match the heat load in your area that's going to serve. If you do not, you're going to be very disappointed. Okay, in this illustration here, it looks like a swamp cooler. This is how a swamp cooler works, or an evaporative condenser, evaporative cooling. It's very simple in nature. The downside of this type of cooling is simply the fact that you're going to have a lot of maintenance involved here. Now, this particular picture here is going to be on page 1064 under 36.6. In this case here, this is a drip type water distribution system where the pump pumps up water, drips into a pad. The water goes down, is going to basically dribble down here, and hot, dry air is going to be pulled in through this panel. And of course, what happens is the air basically is cooled down where it is blown inside the house, shop, whatever. But don't forget, with the swamp cooler, you're going to pressurize a building unless you have a door, a window opening, or a grill to relieve the excess pressure. This illustration is also located under 36.6. In this particular situation, we have a difference. We have a water spray, which is being sprayed. You have a slinger motor that's down here at the bottom, or pumping water out of the sump and spraying the side of this media, I guess we'll call it that. And that in turn, hot outside dry air is being drawn across this panel or media. And of course, we have cooler air being drawn through this unit and supplied inside the building. Remember, evaporative coolers do not work in relative humidities above 30%. So for coastal climate zones such as we live in Southern California, don't even recommend them. If you get out towards Indio, Palm Springs, Lake Havasu, Arizona, I don't care where out there, these things work extremely well, except when you have the monsoon storms come up. This illustration is also located on the same page 1064, and this is a rotating element. I've worked on a lot of these when I worked at Mount Sac Community College many years ago. The shop buildings utilized this technology in order to cool the shop areas. You had a motor that operated at a slow RPM. You had a water trough, which was constructed of stainless steel. You had a water makeup, and basically the water would make up into this tank, and this wheel would take and spin at a slow speed and pick up the water droplets. The fan would take and draw the air through this wheel, which was like a stainless steel, copper brass construction. And the idea being is by that wheel picking up this moisture from the pan down below and rotating at slow speed, you would basically have a form of evaporative cooling, which worked out very well. The problem with this particular design was the water had to be dumped out frequently. Otherwise, it would become slimy, green, mold growth would take place. That was one of the pitfalls of this design. It worked though. Okay, here we have a thermostatic expansion valve. Notice that we have 4 circuits on this particular design here. So on the outlet side of the TXV, you have a distributor, and these are capillary lines going to these individual circuits. We have 4 refrigerant circuits, and of course we have the suction line, which is over here, liquid line feeding the TXV over here. Here we have a and this is found on page 1067. This is a supply and return conditions on a psychometric chart. The absolute humidity drops as a result of reduced moisture content of the cool supply airstream. So what are we saying? If you know how to read this diagram and plot your air conditioning system in the perfect world, this thing should take and remove moisture from the air as it is removing heat at the same time. The result is we have a very comfortable supply air temperature and low humidity. Our human body is designed to function at its best between 45 and 50% relative humidity. If you go and live out in the desert areas such as Palm Springs, India, or Phoenix, Arizona, typically their average humidity conditions out there are 15–20%. And this results in skin drying. This results in very uncomfortable conditions when air conditioning is on, because your skin is very dry, and you're going to have issues with that type of lack of moisture in the outside air in these areas. But again, if you live out in the desert area, evaporative cooling or some type of a device to inject some moisture into the airstream might be helpful to relieve these skin conditions. Here we have a, looks like a rotary compressor. Very simple device, works extremely well. It's very efficient, and in my opinion, they do a good job. You will find these a lot on window units. Primarily, I've seen these on mini splits a lot. They work very well. They're efficient. There's hardly any maintenance to them, and they just function very well. Here we have a distributor, and basically this is going to be mounted on the outlets of the metering device, in this case the thermal expansion valve. And with this distributor, we are going to be hooking up capillary lines to this, and the capillary lines will tie into the individual circuits of the coil. In this case here, we have a lot of circuits on the evaporator coil with this distributor. Very simple device. There's technically no maintenance you're ever going to have to do with these. They work extremely well. Okay, this illustration is on page 1074 of your textbook under 36.22. This basically shows how the stationary vane of a rotary compressor works. So basically, in this illustration shows where the refrigerant enters at this point, and notice that the valve is closed here. We look at this illustration, we have a slider valve here, so the refrigerant is going through this eccentric rotary compressor. And we come down to C, notice that the refrigerant is still blocked at this point, coming through here, being compressed. And then eventually it blocks off the suction port, opens up this side. And of course, the discharge gas is now, the pressure has been increased, the temperature has been increased, so it goes into the condenser where it gives up the heat which was absorbed in the evaporator coil. Okay, this is a R410A split system. Notice that we have a 95 degree ambient suction pressure with 410A. It's going to be 120 PSIG, 448 on the high side. The 446 corresponds to a condensing temperature of 125 degrees for R410A. 95 degrees the ambient temperature in this design picture. 30-degree difference in air temperature, the condensing temperature on a standard grade equipment. So we're talking about a 13 or 14 SEER unit. 125-degree condensing temperature. Last but not least, we have a chart here. If you're not bored with paperwork, well, I don't know what to tell you. When you are designing systems, you need to take a look at this one here is found on page 1070 of your textbook under figure 36.18. And this is basically showing the design conditions for various parts of the United States. So basically, depending on where you live, let's just take Phoenix, Arizona. The latitude at Phoenix is 33 degrees, and it gives you the elevation. It gives you the design dry bulb. Okay, interesting. So the dry bulb temperature at Phoenix, Arizona, dry bulb, they're saying 31. Interesting. At 99%, 34 at 97%, and then at the mean, what they call the dry bulb, wet bulb, 109/71, 107/71, 105/71, and the average daily range from the temperature, the morning temperature and the afternoon temperature, 27 degrees. Design wet bulb. Okay, this is something design wet bulb for an air conditioning system in Phoenix, Arizona, 76 degrees, and the at 2.5%, it's 75, and at 5%, it's 75. So depending on the different design conditions, these are the things that you are going to plot when you are contemplating putting this stuff in your structure, depending on where you live. And of course, it lists different areas of California as an example. Take Oakland right here, gives you the latitude. It gives you the elevation. If you look at Oakland, the elevation is only 3, not very, it's just barely above sea level. And design dry bulb for Oakland, California, 34 at 97%, 36. The average dry bulb is 85/64, and at 2.5%, it's 80 and 63, and at 5% for Oakland, it's going to be 75/62, and then your daily range on Oakland is only 19 degrees, not much, between morning and afternoon sun. Very interesting. And then your wet bulb for Oakland, California, is going to be at 1%. It's going to be, let's see, it's going to be 66. Okay. And then you have 2.5%, 64, and then over here, 63. And that's all I have for today.